Near absolute nothingness, spacetime has a temperature tiny but real, so empty space is not truly empty or silent. By nothing, I mean no particles and almost zero curvature. The surprise is observers still find structure and even heat. Today, we will see what that near nothing looks like. Immediate takeaway: emptiness behaves like a medium with rules. A starless gulf stretches in every direction, cold and quiet. Think of an arena with no bumps and perfect symmetry. Physicists call this ideal canvas Minkowski spacetime, perfectly flat. Flat here means zero curvature, like an endless polished sheet. Light draws straight lines, and time flows evenly for neighbors. Why care about a perfect void you can never visit? Because this is the reference that makes every deviation meaningful. Clocks in uniform motion agree on physics thanks to Lorentz symmetry. World lines are straight, and tidal gravity is completely absent. Light cones match everywhere, setting identical speed limits in space. You push an object gently, it coasts without any surprises. Fields rest in their lowest energy, with no excitations. Real space is never perfect, but small patches get close. Inside a spaceship far from masses, physics looks almost Minkowski. Your weight disappears and rulers keep length as speeds stay modest. Intergalactic voids approach this state, with 1 atom per cubic meter. Curvature there is tiny, practically zero within measurement noise. GPS corrections disappear in this thought scene because gravity vanishes. Even expansion can be ignored locally over short enough times. Rule of thumb: flat space is the clean baseline. Departures from flatness draw the map of everything interesting. So the picture is Minkowski is emptiness with perfect balance. Now add the faintest tremor, the quantum jitter of fields. Even in ground state, fields fluctuate because uncertainty forbids stillness. That jitter is zero-point energy, the lowest hum of reality. Why care here in quiet space with no particles around? Because detectors can be fooled and emptiness can look warm. Accelerate hard enough, a horizon forms behind your motion. That horizon blocks information and the vacuum looks like heat. This is the Unruh effect, a thermal bath from acceleration. The bath temperature scales with acceleration, tiny for human pushes. At 1 meter per second squared, it's about 10 to the minus 20 Kelvin. Crank it to 10 to the 20, you feel roughly 1 Kelvin. No new particles appear, but your detector clicks like warm air. Mechanically, modes get mixed by acceleration, creating perceived excitations. Mathematically, vacuums for different observers are not the same. One sentence recap: motion can turn calm vacuum into fake heat. Quantum jitter also pushes on matter in a measurable way. Put 2 plates close, certain modes vanish and pressure appears. That pressure is the Casimir effect, coming from restricted fluctuations. At 100 nanometers separation, the pressure reaches a few pascals. Small area gives tiny forces, but instruments easily see them. Example: in real terms, microcantilevers bend under this vacuum push. Bottom line: emptiness chatters quietly, and motion hears it louder. Picture an engine pushing you steadily, deep in a starless void. Behind you, a line forms where light can never catch up. That line is an observer horizon, a one-way information edge. Horizon means a boundary you cannot receive signals from ever. Why care? Because horizons make vacuum act like a thermal field. Your rocket sees heat, even when inertial observers see calm. This is the Reindler story, a cousin of black hole radiation. Black holes have horizons too, and they also radiate faintly. Our whole universe likely carries a horizon from dark energy. With positive vacuum energy, geometry becomes de Sitter with cosmic horizon. That horizon gives a Gibbons Hawking temperature, absurdly tiny today. Today's Hubble rate is about 2 times 10 to the minus 18. That yields a temperature near 10 to the minus 30 Kelvin. No one feels that warmth, yet it sets a profound floor. Mechanically, horizons trade inaccessible modes for thermal statistics, like dice. Entropy enters, counting the hidden configurations beyond the edge. Example: a 14 billion light-year horizon sets that scale. Even without matter, geometry alone can make emptiness act warm. One sentence recap: horizons turn vacuum into temperature and entropy. Different observers disagree on that cloak, depending on their motion. Net result: temperature in nothingness is real, yet observer-dependent. Between galaxy clusters, the cosmic web thins into yawning voids. Here, galaxies are rare and the night feels deeper. A void is a region with far below average density. It is the universe's closest approach to practical nothingness. Why care? Because these regions show emptiness under real conditions. Expansion stretches light, cooling radiation that passes through forever, yet a floor remains, set by fossil backgrounds still bathing space. The microwave background stays at about 2.7 Kelvin everywhere. Neutrinos drift colder, near 1.9 Kelvin, whispering through matter. Starlight leaks in, but it gets diluted and redshifted. Mechanically, photons bounce rarely because atoms are vanishingly scarce. Density can be roughly 1 atom per cubic meter here. Gravitational curvature is tiny, so geodesics barely deviate at all. Time flows almost uniformly, with almost no tidal stresses, but the bath of background quanta still sets a temperature. You cannot cool below that bath while the universe expands. Example, the Boötes void spans about 330 million light-years. Through its heart, galaxies are sparse and lines run straight. Travelers would not notice gravity, beyond a faint global drift. Radiation would still warm their instruments above absolute zero. Rule of thumb, real nothingness is floored by ancient light. Bottom line, cosmic voids are cold but never truly empty. Back on Earth, we build chambers to chase engineered emptiness. Think stainless steel tunnels, pumps humming, and cryogenic panels. An ultra-high vacuum means extremely low pressure and molecules. It is space-made lane by pushing gas outward relentlessly. Why care? Because controlled emptiness lets us test quantum claims. Casimir forces need smooth plates, clean gaps, and quiet noise. Modern setups use microfabricated plates aligned within nanometers. Mechanically, pumps remove fast movers, then cold walls trap stragglers. Surfaces still outgas, so time and baking matter a lot. Vibration spoils alignment, so isolation stacks hold everything steady. Many labs hit about 10 to the -7 Pascal. That's thinner than interplanetary space, inside a meter-sized can. The LIGO beam tubes reach about 10 to the -9 torr. Each arm runs 4 kilometers, guiding laser light through darkness. Residual gas still exists, billions of molecules per cubic meter. They scatter photons rarely, but enough to demand great care. Casimir measurements see micronewton forces over micron areas. At 100 nanometers gap, pressure can be a few pascals. That push is small, yet absolutely real and repeatable. Example, atomic force microscopes detect plate attraction while sweeping. Overlaying theory and data, the curve matches vacuum predictions. So the picture is, lab nothing behaves like restless sea. Step back and ask what shape near nothing should prefer. 3 ideal shapes anchor our thinking, with simple curvatures. Minkowski is flat, with 0 curvature and infinite extent. De Sitter is positively curved, with a horizon and temperature. Anti-de Sitter is negatively curved, with a reflective boundary. Why care? Because boundaries decide how vacuum modes arrange themselves. They set which vibrations fit and which ones cannot. Mechanically, curvature sets a length scale that paces fluctuations. In De Sitter, that scale is c divided by h today, that is about 14 billion light-years across. Modes larger than that effectively freeze and feed classical structure. In anti-de Sitter, waves bounce inward, shaping standing patterns. That playground connects to holography, where boundaries encode interiors. Minkowski sits between them, with no preferred global scale. Then there is the Planck frontier, where geometry may foam. Planck length is about 1.6 times 10 to the -35 meters. Planck time is about 5 times 10 to the -44 seconds. Energies there scramble smoothness, and space may twitch violently. We are far below that by many orders of magnitude. The Large Hadron Collider reaches about 10 to the 13 electron volts. Planck energy sits near 10 to the 28 electron volts. That gap is huge, roughly 15 orders of magnitude away. Example, any foam would blur light arrivals at imperceptible levels. Bottom line, geometry and limits choreograph what nothing can do. So near absolute nothingness, spacetime stays busy and warm, not warm for us but warm by deep principles. Horizon heat, quantum jitters, and geometry give emptiness structure. That was the payoff hiding in our opening line. If this reshaped your picture of nothing, stick around again. Subscribe for more cosmic clarity and bring a curious friend.